We're the Mid-American Geospatial Information Center, or MAGIC, Emergency Preparedness Team. My name is Emma Arsakin. I'm a rising junior from Houston, Texas, and I'm interested in theoretical physics and astrophysics.
My name is Rebecca Catinghead. I'm a rising junior from Dobbsbury, New York, and I'm interested in biomedical engineering.
Hi, my name is Rajesh Sharma. I'm a rising senior from South Brunswick, New Jersey, and I'm intending to major in aerospace.
My name is Garza. I'm a rising senior from McAllen, Texas, and I'm interested in aerospace engineering.
And I'm Evan Agarwal. I'm from San Diego, California. I'm going to be a senior as well next year. And before I came to Texas, I thought I wanted to major in aerospace engineering, but now I'm not so sure anymore.
So before we get started, I would like you guys to just take a second and imagine that if you were a leader of a country that just got hit by a devastating hurricane and there is a significant amount of property damage and a high death toll, what would you exactly need to do in order to help your country and save your people? Any thoughts? Ideas?
Think of ways how to help them, like maybe find out like evacuation routes or something like that.
That's a good idea.
Anything else?
You need to know exactly how much damage is done. You have to know where to go first.
That's good. Yeah, that's essentially on the right track of where our project is leading.
So to understand this question a little better, you need to know what emergency response is. And essentially, it's an organized reaction to a large-scale disaster. This can be an earthquake, flood, tsunami, or any other natural event. It's usually done as a humanitarian effort to help those who have been displaced or harmed by an event. And responders often use satellite imagery to help them figure out what's going on, where it's happening, and what to do next. So one of the biggest tools that scientists and emergency responders use is remote sensing. And this is essentially scanning the Earth via satellites instead of traveling physically on site to collect data. And sensors on board satellites can collect data in many different wavelengths, such as visible, infrared, microwave, and various others. And each wavelength provides a different kind of data. For example, the Sentinel-1A satellite uses a microwave radar to scan through cloud cover and night.
Okay, so going back off of emergency response, founded in the 2000s, the International Charter for Space and Major Disasters was founded by the French space organization at ESA, otherwise known as the European Space Agency. And essentially their goal is to provide humanitarian coverage through satellite imagery in order to target impacted areas by disaster. Currently there are 15 major space organizations and more incoming. And they essentially take the satellite imagery, analyze it, and give it back to the nations that need it. And over here what we see is a charter geographic tool, and essentially it keeps track of all the different areas that disasters have occurred, and the International Charter has been activated to help these nations. And also recently the International Charter has been involved in man-made disasters such as the 2010 Gulf of Mexico oil spill and the Malaysian MH370 air flight downing. And also as of 2012 they enacted the Universal Access Policy, which allows any nation, whether or not they're part of the International Charter, to get satellite data and help for their disasters. And what you see over here is the cyclical process of how the International Charter actually functions. So when a disaster occurs down here, it goes to an authorized user, which basically lives in the nation and is firsthand experiencing the damage done by the emergency. And it goes to an on-duty operator, which was working 24/7. So the International Charter is available whenever someone needs help. And the on-duty operator essentially verifies the authorized user and takes in any of the information needed about what's going on. And then that gets passed on to the emergency on-call officer, which takes all the information from the on-duty operator and basically organizes the data and manages it. And that is useful for the charter members, which are essentially the different space organizations that provide the satellite imagery, so they know where to target their satellites and where to effectively maneuver them. And eventually, in the end, this goes to the value-added specialist, which takes the satellite imagery done by the charter members and analyzes it and breaks down if it's a flood, if it's a hurricane, what the damage is actually done from space. And in the end user, again, the nation realizes that they can use now the satellite imagery, analyze it, and analyze it sometimes further, and then apply that to their nation. And overall, this whole process is managed by the project manager. And a couple things that you may find surprising is that NASA is actually not part of the charter members. And the reason that is because NASA is a space research organization. They don't necessarily collect satellite imagery to be used for Earth, but there is a United States-based organization that does do that. And another thing is that the project we're working on is considered under the value-added specialist, which you will find out later why.
Okay, so the USGS, or the United States Geographical Survey, is a scientific agency that is monitored by the US government, and is also the organization from which we obtain our images and data that we analyze throughout the project using the Landsat 8 satellite that is orbiting around Earth and that they are currently monitoring. And so essentially what the USGS does is they provide continental landmass coverage of the United States and other areas of North America so that they can relay these high definition images to first responders and send this information to them so that they can allocate their resources in appropriate areas to communities that may be prone to natural hazards. So I want to talk a little bit about the mission areas that the USGS focuses on. The first one is the climate and land use change area. And so what they do here is they track how the climate changes, essentially tracking the different trends throughout the years and extrapolating to see how it may affect us in the future. They also keep track of how we use our land and how we can redistribute it more effectively. The second mission area is the core science systems. And so what the USGS does here is to keep track of the Earth's complex and biological systems. And what I mean by that is to keep track of what goes on underneath the Earth, how it behaves, and they keep track of a lot of the earthquakes as well. They interact with other international space agencies to keep track of seismic activity. And so the third mission area is energy and minerals. And what the USGS does here is they track the different energy resources that we have. They see where they are, how we can obtain them, and maybe even research new ways to obtain different energy resources. And finally, I believe the most important one is natural hazards. And so, like I said, they provide high definition images of different natural hazards. And so they can provide images of earthquakes, volcanoes, hurricanes, and floods, which is what we essentially were studying in the images of the Houston flooding to explain later.
So as Samia mentioned earlier, every international charter member has a space resource that they contribute to the charter. And in the case of the USGS, that space resource is the Landsat satellite. So the Landsat was a collaboration between NASA and USGS. It was designed, built, and launched by NASA, but today the ground operations and data flow and all that control is monitored by USGS. And something I thought was kind of cool was that since the satellite is a government asset, you and I and technically all taxpayers are technically owners of the satellite. So the satellite orbits Earth every 16 days and can take up to 550 images in just one day. And those images have so much information that the file size is as big as 1 gigabyte. And so each image stores all of the information in 11 bands, and the information is collected by the 2 onboard sensors on the satellite. So the first one is the Operational Land Imager, also known as OLI, and OLI collects information in the visible, near-infrared, and shortwave infrared wavelengths, and all of that information is stored in bands 1 through 9. The second onboard sensor is the Thermal Infrared Sensor, also known as TIRS, and TIRS collects information on the land surface temperature, and that information is stored in bands 10 and 11.
Okay, so going off of what Evan said before about satellite images being 1 gigabyte, and the reason for that is the resolution size. And resolution is technically categorized under a way that you would classify your satellite imagery. So the first one I'm going to talk about is spatial resolution, which is in simple terms basically if your image is high resolution or low resolution. If you want a high resolution satellite image, that basically limits to a very small area of land, but your pixels are very detailed. On the other hand, if you want a very large, massive area, it's going to be causing you to go into low resolution, otherwise your pixels are going to be very distorted. Another way you can classify your satellite imagery is through temporal resolution. And also, as Evan mentioned before, the Landsat 8 satellite covers a specific point on Earth every 16 days. But on the other hand, a satellite called MODIS covers a point on Earth every 1 day. So essentially, how fast does a satellite return to a specific point and image it again? That's basically your temporal resolution. And the combining point of these two factors is essentially how big is the swath that the satellite is covering on Earth is going to decide whether it's high or low resolution. And the final thing that's, I guess, the most important for our specific project is the spectral resolution. Now, for right now, I'm not going to talk about broadband and ultraspectral because that doesn't really apply to us, but the two main ones you should probably focus on are multispectral and hyperspectral. So for those of you that know the electromagnetic spectrum, it basically varies from different types of lights with their different wavelengths. And multispectral is basically classifying the electromagnetic spectrum into different portions. The multispectral one has very large portions, so the colors get categorized in much larger chunks. While on the other hand, hyperspectral has much more thinner and finer chunks. One would use hyperspectral data if they wanted to see land masses such as water versus land. But you would use hyperspectral if you want detailed things like specific species of vegetation or geologic mapping.
So we use these multispectral bands to analyze satellite imagery from the Houston floods from this year. Now this was a series of floods running all the way back from March well into June, and we focused specifically on a period of time in late May. So this was the worst flooding disaster in the Houston area since Tropical Storm Allison in 2001. It resulted in 11 to 22 inches of rain. An estimated 240 billion gallons of water fell over the course of only a few days. And all of this resulted in 11 deaths, thousands of people displaced, and billions of dollars in property damage. So since this was such a huge catastrophe, the International Charter was activated in response.
So our goal as a team was to take these raw images from Landsat and transform them into something that we could use to easily and visually analyze the extent of the flooding. And in a professional situation, we would then take those transformed images and create maps from them and give them to emergency first responders so those first responders could assess where and how to begin their work.
Okay, so the tool that we use to analyze the images and data that we received from Landsat 8 is called multispec. And through multispec, what you can do with these high-resolution images is categorize certain pixels into one area and classify them. So if you wanted to distinguish between different topographical characteristics such as clouds, land, vegetation, or city, you can do it with multispec using classifications. And so the reason it's called multispec is because it can analyze images in multiple spectral bands, ranging from 1 through 7. But it can also go up to hyperspectral data from AVIRIS and the MODIS instruments. Another great thing about multispec is that when we categorize water in the area, such as in the Houston area, we can find the percentage and the area that it covers in that image in order to see the true extent of the flood.
So essentially what we were doing with multispec was creating a thematic map, which is basically an image which is sorted by color depending on the land underneath it. So for our purposes, we were separating water and the rest of the land so that we could clearly visualize the extent of the flooding.
So now that you know what multispec is and kind of what it does, we'd like to do a short demonstration on how we classify an image. We didn't want to open up the actual program because it takes such a long time to classify one, so you get screenshots instead. So this is what pops up when you first try and open an image. This is us opening a raw image from the Landsat 8 satellite. And what you can see over here is the different channels that you can set for the image. Now, we have the red, green, and blue set to 4, 3, and 2, which is the default visual bands of the image. So this is what it would look like in a regular light. And that would pop up something like this. But this can be kind of hard to classify, so it might be better for us to change the channels. So for our purposes, we would change it to something more like 671, which alters it to something like this, which you can see, it can be a little easier to see the water than in the previous image.
So once we've decided on our channels, we need to collect the training sets. So we collect the training sets by selecting an area of pixels that we want to designate as a specific feature. So that might be land, water, or clouds. And in our case, it was really important to do those three because we're working with water. We want to see where the water is. Because each feature has such a variety of pixels in it, and it's all over the map, we need to make sure that we collect many, many training sets just for even those three features. So you can see in this image, I think there's probably 40 or so training sets just to classify water and land alone.
Okay, so essentially what you see here is the thematic image once we make the training sets. And right now it kind of looks like a circus clown mess because every single class that we created has been assigned to a different RGB value, which stands for red, green, blue pixel colors. So in order to see where actually the water is, we're gonna open up the color file, which is in a sense kind of like coding. So what you see right now is the different class numbers on the leftmost, and then the 3 RGB values going down the center, and then the class that's been assigned to the specific RGB value. So now over here, since we want water to be one color and land to be another color, we're going to set water as 3 specific numbers and make all the water classes that, and anything to do with land such as city, vegetation, and bare land to be another set of colors. And what you see over here, the G2, you may be wondering what that is. So that's essentially like setting a variable. G2 is a group. So classes go under these groups as subsets. And the water is assigned to the same watercolors in the classes. So that way, if you want to have a quick access to the 2 variations you have, you don't have to go through all the different classes.
Okay, so in the end, we get this final thematic image, and as you can see, the water is clearly highlighted with light blue, and then the rest of the image is in orange. And so what the program does is it goes through a statistical analysis and classifies all the pixels that we specified as water under that one color, and all the rest of the pixels that we classified as land as that color. And so you can clearly see the extent of the flooding when you compare images before the flood and after the flood.
So when we started our project, we were each given 2 raw Landsat satellite images. And our goal was to turn these 2 images into thematics so we could use them to analyze the extent of the flooding. And both of these images were taken of the same place, but at different times. One was taken March 25th before the flooding, and one was taken on May 28th during the flooding.
Okay, and here we have another set of tiles, which are directly below the area that we had previously mentioned. And so again, here is the original and thematic image from March 25th before the flood, and the original and thematic image from May 28th during the flood. And so you can see the extent of the water over here and how it has spread out over time.
Here's another set, and in these 2 particular images, it's really obvious to see the flooding. You can see how much more water there was in the image from May 28th, than there was on March 25th.
Again, we have Again, we have another set of tiles here. As you can see, the Brazos River is normal over here, but during May 28th, it has really expanded its water.
And just, again, more water on May 28th than there was on March 25th.
Okay, so in the end, we would put all our images together in a process known as mosaicing. And so basically, we put all the tiles, overlay them so that we can create one big image. And so here we see the March 25th images, the original and the thematic ones that we created. And then here we have May 28th after the flood. And so although there is a lot of cloud coverage, which can obscure some of the water, we can still see through it with multi-spec, which is why multi-spec is ideal in order to see the extent of the flooding.
So this slide here is really the culmination of our work together as a team. It has the 2 thematics, the one from before the flood and the one from after. And you can use them to compare and really, really see the difference here where there's a lot more water on the 28th than there was on March 25th.
Okay, so another way that we can analyze this flooding is by looking at aerial images. So what I did was I went on the Magic website where they kind of have like an interactive thing where I can overlay the Houston area with an image taken by JAXA, which is the Japanese Space Agency. So that's this black and white image. And this really shows the darker area, which is the water during the flooding. I can also overlay it with images from the Texas Civil Air Patrol, which is TexCAP. So those are those blue dots. And when I click on those blue dots, an image will come up. So, for example, these 2 images clearly show flooding. So what I was doing here was kind of editing this map. So, for example, if I click on this point here, this image of this house will come up, and that's pretty striking. That's obviously flooded. But if I zoom in on that image to find that house, a blank field will show up. So where is this house? Actually, it's over here, not where the website said it was. And that's because these images are being taken from a plane. So when these images are being taken, the coordinates that are being recorded are at the position where the plane is, not where the actual image is. So my job was to find these images, find the actual spot where they were, record the coordinates, and then sort of put them into a text file, which then I could insert into a program. This is another example of how far off these points can be. So this is a point that comes up with this image, which is not anywhere near where it actually is. It's actually way up here. So what I did was I record the points, I record the URL, and then I give it a number. I plug it into a program, and it becomes this instead of this. So I didn't select all of these points because they were actually sometimes hard to find. But I selected 15 and put them into a map.
So over the course of this internship, we did run into a few struggles and challenges we had to overcome. One of the biggest ones at first was that our image training sets were sometimes hard to combine into groups. For example, if we had 6 or 7 water classes, at first we couldn't combine them into one water group, so we would have 7 different colors of water. Another thing was that pixels sometimes registered as the wrong thing. A really common one was that cloud shadows would register as water when they weren't. And images often had to be viewed in different channels so we could see them and classify them clearly. That was the RGB I mentioned earlier. Blank portions of the image that were cut off sometimes registered as actual data, which kind of confused our results a little bit. And Rebecca had a problem with the TextApp images because they were sometimes hard to put in their actual locations, since there weren't really many distinct prominent features on the land that you could use as reference.
So here are some of our wrap-up questions. What did we learn from this project? Well, obviously we learned a lot about remote sensing and emergency response, but in addition to what we just shared with you, I know I learned a lot about working in a team. Like a lot of the other groups said, it was really exciting and humbling to work with some really intelligent and really motivated students. But with intelligence and motivation comes a lot of really strong opinions, and so I think at first it was a challenge, but it was really important for us to learn how to compromise and to come to consensus on how to do this or how to do that. And it was important to the success of our project, and I think in the end we did a good job working together, and I had a really great time with these guys. So an amazing team.
So was the program worthwhile? Yes. I cannot say yes loud enough. A lot of people have mentioned, I know you've heard of Marsbound, that wonderful piece of art that was Marsbound. Even though it was stressful and we kind of didn't want to do it for a while, it was really beneficial to us because we learned how to operate under stress. Another big thing that people have mentioned, I think every group has mentioned this, the Johnson Space Center. I'm from Houston. I've been to the Johnson Space Center I don't even know how many times. So when they said we were going to the Johnson Space Center, I was kind of like, okay, I'll go. It was the best experience of my life. That was the best day of my entire life. Wow, I've only ever seen the really commercialized parts of it, but we actually got to go behind the scenes and see the real science behind the Johnson Space Center. It was incredible. And then, of course, there was the experience of working with all these wonderful, intelligent interns and the scientists who know so much about their fields. It was incredible, and I would recommend it to anyone to apply.
Okay, so any suggestions for future programs? I would say that the program is fine as it is because I believe it was truly amazing. But if I had to make one suggestion, I believe it would be to make it a little bit longer, maybe extend it a week. So that way we could conduct more research and get to activities that we never really got to for Marsbound and stuff like that. So I believe that extending it would really allow us to collaborate more with our mentors, conduct more research, and in the end present more findings with all of you guys.
Okay, what was our overall impression of the program? So I think I speak for everyone when I say this. It was probably one of the most life-changing experiences probably any of us will ever go through as a young person. And for one of us to originally go through Johnson Space Center just to be walking in the glass walls and kind of scroll right through the ISS, versus actually being able to touch the sweaty chairs of the old mission control and walk into the tiny fetus-looking Soyuz capsule, it really makes an impression in your brain that, you know, this is something you want to do later on in your life. And even if you may be staring at your screen for YouTube for hours and hours, you should probably stop that and maybe pick up and learn something about space, because it's going to help you later on in life. And overall, I think no one would ever regret doing something like this. It's just fun.
Okay, so how did the program influence our future? I can't speak for everybody, but for me, this really solidified my interest in STEM. Like, I didn't really know what I wanted to be going in, but now I definitely know that I do want to do something STEM, probably engineering.
Okay, what was our personal takeaway from this project?
Yeah, I said a little bit earlier how when I came to Texas, I had been thinking about studying aerospace engineering, and these past 2 weeks kind of changed that thought in my mind. So I guess I love STEM, and I love the idea of space exploration, and I really like the idea of maybe one day working for NASA or a similar company. So in my mind, studying aerospace engineering was the way to accomplish that goal. But these last 2 weeks here in Texas have shown me that there are so many things that I could do to be involved in space exploration or work for NASA and be in STEM. So like when we went through Johnson Space Center, we saw so many different scientists from so many different fields and so many different engineers, and they had all types of people. So it sounds kind of cliche, but I think this program really taught me that I should follow my dreams and like study what I want to study and do what I want to do, and not just work for the job.
Yeah, it definitely like expanded my horizons. Also, it taught me to keep on working hard, because like I met all of these kids and they were all so multifaceted and talented. And it wasn't just STEM that they were interested in, and as well as the scientists here, we're all very hardworking, all very knowledgeable, and you really can't be a slacker to do that.
My personal takeaway from this is that I really got to see how different organizations and people work together. So when you think about emergency preparedness, you only think about the first responders and getting to the communities that are devastated, but going behind the scenes, no one really thinks about remote sensing and the jobs that the CSR does and NASA does to assist in emergency preparedness. So I thought this was really eye-opening experience, especially working with Mrs. Howard was awesome. She's an expert at what she does, and learning from someone that knows so much was really an amazing experience. I have to say also, I think one of my favorite parts of this program was going to the Johnson Space Center. I cannot stress enough how amazing it was. Going down to see all the different robots and the rovers that they were making was truly amazing, and really solidified my idea of studying aerospace engineering. Also hearing from exceptional scientists such as Norman Chaffee, who was a chemical engineer on the Saturn V rocket, really inspired me to work hard later in my life and pursue a career in STEM.
Okay, so my personal takeaway from this project is probably me being more stubborn on wanting to major in aerospace engineering. Like before I walked in, I was like, yeah, you know, you kind of build rockets, you go to the moon, stuff happens. But after this, I was like, there's a lot of steps to this. Like in the Saturn V rocket, there's at least like 3 to 4 different stages of deployment before you actually reach to the moon. So, and also another interesting thing was that aerospace is not strictly like sending something to Pluto. No, it's like you can build drones, you can go underwater, you can be a diver in the neutral buoyancy lab. So what I understood was science is not just this one specific thing. It's a multifaceted collection of everything that you learn in life and coming together. And that's what an engineer does. It's taking everything you learn in life and like applying it to real life problems.
So on that track, this internship really taught me a lot about NASA, the administration as a whole. It taught me that NASA is not just sending stuff to the moon and putting a rover on Mars, as one other team said. It's so much more than that. It has so many practical applications on Earth and immediate results. When I came into this program, I was kind of, and I still am, fixated on physics and astrophysics, and everything else was like, okay, that's science, I guess, but I'm really interested in physics. And I was, of course, so ecstatic when I got the internship, but, you know, like, okay, it's not physics, but it'll do, I guess. And then I got here, and I was blown away by how much fun this was and how this is actually impacting people. And it really taught me not to close myself off in just one field. It taught me to open my eyes and broaden my horizons, because there is so much interesting stuff in science. And of course, I cannot say this enough. It was so incredibly humbling to work with Ms. Howard, to work with all of the NASA staff. It was the best experience of my life. My mom is watching this. She can attest that there were 2 times in this internship when I told her I was having the most fun in my life. Yeah.
So thank you. Huge thank you to Mr. Zahara for mentoring, guiding, and teaching us over the past 2 weeks. We had an awesome time working with you. You taught us so much. It was really, really good to work with you. And then,
Also, special thanks to Mrs. Baggio for organizing all of this. It was truly amazing. Everything was on point. It was just really, really great. And so, also thanks to all the CSR staff and the CES teachers as well. Shout out to Tom and Leo for always keeping track of us late at night. And thank you to my parents as well who are in the back, because I would not be here without them. And thank you to all of you CES interns for being with me along on this great experience.
So I'd just like to thank the University of Texas for providing the most economically cheap gym for me to stay in shape, and a very, very good dorm that was mostly controlled at the right temperature. And Center for Space Research for opening my horizons and just making it seem like, you know, space isn't something that's really far away, it's something attainable. And to the Texas Space Grant Consortium for sponsoring kids that don't live in Texas to come down here and learn about something that wouldn't be possible in their state.
Again, just mad props to everyone who organized this. This was so incredible. It was the best experience of my life. NASA, of course. NASA, thank you for funding us. Thanks for the money and the experience.
Questions? Yes.
When you were classifying the data, did you have to go like pixel by pixel, or did you have something that would just like guess and
Like
set it
you
for
could
you?
just click and drag.
yeah, it was a lot like Photoshop, like the selection tool. You just click and drag a square. It was pretty easy.
So everything within that selection would be classified as one type of like water or something.
I mean, you want it to be as small as possible, though. Like, you don't want to do it over a large area, or else your data is useless.
You don't want to mix water and land, because there's a lot of like little lakes and stuff. So you just gotta make sure you're just selecting water or land.
Because on Earth, each and every single pixel, well, Earth's not made of pixels, but when the picture is taken, it's made of pixels. So each pixel is not going to be the same color. Water varies in its color. So you can pick a specific area of a lake and assume that's going to cover every lake. No, that's not the case. You have to pick multiple lakes. That's why you end up having 40 or so classifications and having like a jumbled up color mess that you have to fix.
It takes a long time. It's bad.
Yes.
So along those same lines, did you guys have to train each image, or did you just do one and then do all 4 or 5 in your mosaic?
You have to
Each
train
image.
each image.
Each one.
Yeah.
Because each one has a different, like, they're all slightly different hues, especially with the water.
Yeah, and some of the images, like there was a lot of clouds. So some of the clouds would have like some blue pixels in them. So if you would like catch one of those, that would be classified as water. And so you would have to go back, delete that class, and redo it again, like isolating a certain amount of pixels.
So based on your experience and what you learned, how do you think this experience and with your career future paths can help the environment deal with such type of disasters?
So basically our project is essentially relating to that question. NASA not only goes to space, but they're heavily focused on climate change, and our project emphasizes that very clearly. If we're going to continue destroying the Earth by emitting greenhouse gases and CFCs, we're going to have more floods, more natural disasters, and the sea level is going to rise, potentially flooding more and more areas. And the process that we went through allows us to target a specific area and see where we need to respond. But if we're able to protect the Earth and avoid these type of disasters, we can save money and resources.
And like if you watch the news or Weather Channel or whatever, and you see images of the land, it doesn't look like regular satellite imagery because that's really hard to analyze. Instead, they use the kind of thematic images that we were actually making during the internship. So that really allows not only scientists but the general public to easily view what's going on in the area and act on that information.
Any more questions?
Any other questions?
Good job.